Hi everyone, welcome to this M2D2 talk. Today we have Leslie with us, and he'll be presenting his recent work on Interpretable Chirality-Aware Graph Neural Network for quantitative structure-activity relationship, modeling in drug discovery. Thank you so much, Lance, for accepting our invitation today. And before we start, a few words about Lance. Lance is currently a PhD student in the Miller Lab and the NDS Lab, where he's advised jointly by Professor Jens Miller, Tyler Dare, and Bobby Bodenhammer. His recent research focused on developing novel state-of-the-art deep learning methods that are specifically designed for small molecule and drug discovery applications. Once again, thank you so much for accepting our invitation to present your work here today, and looking forward to it.
Thank you, Prudential, for the kind introduction, and thank you for the invite for this talk. Yeah, so hello, everyone. My name is Yunchao Liu, and I also go by Lance. I'm from the Vanderbilt University. Today, I'm happy to share a new graph neural network called MolKGNN that we designed for the drug discovery campaign. So during the talk, if you have any questions, feel free to interrupt me, and I'm happy to answer the questions. So yeah, let's start. First, we will start with something we are all familiar with, the SARS-CoV-2, aka the coronavirus. So recently, Pfizer have announced that they found a medicine called Paxlovid. So in this medicine, there is a small molecule that can potentially treat the disease. So this small molecule can bind and inhibit the function of a target protein called 3CL protease. And this target protein is very essential for the viral replication. So in a similar fashion, for a certain disease, scientists will first try to identify some targets that are related to the disease. And then they will try to find some small molecule that can bind and alter the function of this target. So by binding and alter the function of this disease-related target, this small molecule eventually treat the disease. So the problem is, how do we find this small molecule? Traditionally, scientists will use some automated equipment known as the high-throughput screening equipment to screen through a very large number of chemical libraries and find some possible active molecules. However, this brute force method has a very low rate of finding active compounds. Usually, this hit rate is estimated to be less than 1%. So one way of improving this is to use the data from the experiment and train a graph neural network. And we can use the trained graph neural network to screen a much larger virtual library. Then for these predicted active molecules, we can focus on them and prioritize them for the further experimental validation. So in this study, we view a molecule as a graph. Basically, the nodes are the atoms, the edges are the chemical bonds, and both the nodes and the edges have attributes. So here, I will give a little bit more background on what graph neural network is. Most graph neural network use this neural message passing scheme. Basically, for the graph, if we look at a center node and its neighbor, we prepare a message from this center node along with its neighbor. Then we use some permutation invariant functions to aggregate those messages. Usually those permutation functions include like max, sum, or average. And finally, we update the center node's state using the aggregated message. This process is repeated several times so we can reach the neighbors several hops away. The key idea here is to generate a new node embedding of the center node by aggregating the attributes of the neighboring nodes. However, as we mentioned earlier, graph neural network uses a permutation invariant aggregation. That means graph neural network cannot distinguish different ordering of the neighbors. As you can see in this example here, if we have neighbor number 1, 2, 3, or if we permute it to be 2, 3, 1, these two does not make any difference for the graph neural network. It views it as the same thing. However, for us, the neighbor ordering is important, especially for those chiral molecules. Chiral molecules are those that cannot be superimposed on its mirror image. They cannot be superimposed by translation or rotation, just like our left hand and right hand. Here, I will give you a little bit more background on why this matters. As we have mentioned earlier, small molecule binds to the target, usually in those cavities known as the pocket. If we view it in the 3D, say we have chiral molecules and we want to put it in the pocket, just like putting our hands in the gloves. It's okay for us to put our left hands into the left glove, so does the right hand. But if we reverse the pocket or reverse the glove, we can see it probably won't fit. One classical example of this chirality problem is from the drug known as thalidomide. This drug was initially prescribed to pregnant women to control nausea and vomiting in 1957. And then this drug was withdrawn because it was evident that it caused babies to be born with deformed hand and limbs. Then in late 1970s, studies indicate that the R configuration of thalidomide is an effective sedative, while the S configuration of thalidomide causes fetal abnormality. So as you can see here, these two molecules only differ in the small region highlighted by this red circle here, yet they have a very different therapeutic effect. So this highlights the importance for our model to be able to distinguish chiral molecules. And here, just as a side note, for this specific molecule, latest study also found that these two forms, they can undergo in vivo metabolic inversion to each other. So now let's look at some previous methods that try to distinguish chiral molecules. Some previous methods, they try to do some operation in the aggregation function. Like in this method shown here, they try to list out all the permutations and have all these permutations considered so they can distinguish them. Some other methods also try to consider different angles. So here we try to propose a new design to distinguish chiral molecules by using molecular convolution. To talk about the intuition of molecular convolution, first let's look at image convolution. Here I showed an example of edge detection. So basically in the image, if we try to detect the edge, we can look at the image patch and convolve this with some kernels, and we can do the image convolution. Basically, the image convolution is to multiply the values in each pixel in the corresponding values in the kernel and sum them up. And we can get a convoluted value like 20 here. We can also use a different kernel to do the convolution. As you can see here in the example, we can use a horizontal kernel to do the convolution. There are several observations we can make from this simple example here. First, the higher the convolution value, the more similar a pattern is to the kernel. As you can see in the example, the image patch shows a vertical pattern, and it's more similar to the vertical edge kernel. And secondly, we can observe that the patterns in the kernel can also offer some interpretability. Here, I also showed an example in the face detection task. As you can see here, in the face detection task, the kernel can reveal different patterns in different levels, like the low level probably detect some edges, medium level detect some nose, eyes, and the high level detect some human face. So in a similar fashion, if we are given a molecule, we also want to look at a molecular neighborhood. Here, the molecular neighborhood is defined as the one-hop neighbor to a center node. And we want to convolve this with a molecular kernel. What we want from this molecular convolution is a similarity score that quantifies the similarity between the molecular neighborhood and the molecular kernel. There are several properties we want from this molecular convolution. First, similar to the image convolution, we want the more similar neighborhood to the kernel, we want the score also to be higher. And secondly, this molecular convolution should be rotation invariant. This is different from the image convolution because in image convolution, we don't have to have this rotation invariance. And finally, we can see that this molecular kernel also offers the benefit of interpretability, just as the image convolution. I see a raised hand, so Prudential.
Yes, maybe there's something I'm missing, but if it's rotation invariant, how do you take into account the order then?
Rotation invariant doesn't mean it's permutation invariant. Yeah,
Okay, sure.
so yeah.
Yeah.
That makes sense. Oh yeah, sure. Okay, so I continue. So now we have molecular convolution. Next, the question is, how do we calculate this similarity score? How do we do this molecular convolution? Basically, we divided this similarity score into 3 subscores. The first is the center subscore. The second is the neighbor subscore. And the last one is the edge subscore. And in the end, we want a weighted sum of these 3 subscores. And here we enforce the degree of the neighborhood and the kernel to be the same. If the degree is not the same, then we say there's no similarity between them. The similarity score is set to 0. Now let's look at the specific subscores. First, the center subscore. So the center subscore quantifies the similarities between the center atom attribute similarity. So we can use the similarity function to quantify these 2 attributes. So here for the similarity function, we use the cosine similarity, and these attributes, they are basically vectors. So we can use different vector similarity metrics. And then we look at the neighbor subscore. For the neighbor subscore, we look at those neighbors. So here, for example, the x1, x2, x3, and the corresponding x1 prime, x2 prime, and x3 prime. So here we first align them. Like here, the example, we align x1 with x1 prime, x2 with x2 prime, x3 with x3 prime. But you may wonder, is this the best way to align them? Yeah, that could be multiple ways of aligning them. Here is another example. For example, x1 can align with x3 prime, x2 can align with x1 prime, and x3 can align with x2 prime. So basically, we enumerate all of the possible alignments and find the one that gives the highest score to be our best alignment. Then a natural question would arise. If we want to enumerate all alignment, would that be computationally prohibitive? What if like an atom has 100 neighbors? Then if we try to find all the alignment, that just becomes computationally undoable. Well, luckily from the domain, we have some constraints. So if we look at drug-like molecules, we know that we don't need to look at the whole periodic table. There are actually only a limited number of elements that we need to consider. And for this limited set of elements, they only have a maximum neighbor number of 4. And here some of you may ask, wait a minute, like the sulfur can have 6 bonds. How can it have a neighbor number of 4? Well, even for an element like sulfur, it has double bond to its neighbor. So the double bond count as 1 edge. So still, these elements, they only have a maximum number of 4 neighbors. And moreover, the number of atoms with 4 neighbors is comparatively fewer than the atoms with 1 or 2 neighbors. So in general, we don't have a large computation cost from this enumeration of our alignments. Okay, that's for the neighbor subscore. Now we keep looking at the edge subscore. So for the edge subscore, we similarly, we use the alignment from the previous step because those edge and the neighboring nodes, they have correspondence. So we use the best one from the previous step, and we calculate the average edge similarity between those edge as exemplified here as E1, E2, E3. So once we have this similarity score, then we can start to look back to our previous question. How do we distinguish the chiral molecule here? The key idea here is to use a reference, and we compare the orientation of one of the chiral molecule to this reference. And if this is of the same orientation, then we give it an indicator of 1. If it is of a different orientation, then we give it an indicator of -1. Then we can multiply the similarity score by this indicator. So we can have 2 different similarity score for different orientation of the chiral center. So the way we use to calculate this orientation is this signed tetrahedral volume. So basically, we can construct 3 vectors from the 4 neighbors. We can choose arbitrarily these 4 neighbors, and we construct them, for example, here, A, B, C vectors. And we can calculate the signed tetrahedral volume by doing 1/6 times the A vector cross product B and dot product C. And this one can give us a signed tetrahedral volume. Can be both positive and negative. And notice here, in the actual calculation, we probably do not need the 1/6 because we care more about the sign, which indicates the orientation. Once we have the orientation of these neighbors, then we can do the comparison. For example, here we have neighbor 1, and we can calculate the signed tetrahedral volume and compare it with the signed tetrahedral volume with of the kernel. If they are of the same sign, that means they are of the same orientation. Otherwise, they are of the different orientation. I see a raised hand there. So
yeah, is this the tetrahedral volume can be replaced by some other volume, some other shapes?
By some other shapes. Well, so first of all, this chiral center only happens when a center atom has 4 neighbors. So if you have 4 neighbors, it's a tetrahedral.
Okay.
Right.
Yeah.
Yeah. If you have 3 neighbors, there is no chirality problem there. Yeah.
Okay, thanks.
Yeah, no problem. Yeah, that's actually a good point. Actually, when we do this comparison, we also checked whether they have 4 neighbors. Also, we check if any of the 2 neighbors are the same. Because if any of the 2 neighbors are the same, by just rotating, you can always convert one orientation to the other. So yeah. So only when all 4 neighbors are different, then we have this distinguishing chiral molecule problem. Okay, yeah. Good. So once we have this tetrahedral volume, we have introduced most parts of our method. Now let's look at the overview of the whole method. So as we mentioned earlier, our method is known as MolKGNN, which is short for this Molecular-Kernel Graph Neural Network. So basically, for a given molecule with n atoms, if we look at its molecular neighborhood, and we can want to convolve this with a set of kernels. Here I use M kernels, and those kernels are learnable, just like in image convolution, those image kernels are learnable. So here we have different degrees of kernels, kernel 1, 2, 3, 4. As we mentioned earlier, at most we go up to a degree of 4. And we convolve them, we can get a set of similarity scores. So here, instead of like in traditional graph neural network, where this message is made from the neighbor attributes, here, instead of the neighbor attributes, we use the similarity score in the neighbors. So like this 0.9 means that the neighborhood is 0.9 similar to the first kernel. So here we have n rows representing the n atoms, and we have m columns representing m kernels. Once we have this message, then we can do the message aggregation, and we can update to get a new center atom attributes, and we can go on to the next layer, just like in the traditional graph neural network. Okay, here's the model. Now we need to evaluate our model. Yeah, Prudential.
Yes, I was wondering, how do you have multiple kernel sizes, or do you have one specific like kernel size you use across all the different part of the graph?
You mean the number of kernels for each degree, or
the size of the kernel itself?
The size is always one hop neighbor. One hop neighbor with different degrees.
Yeah, but like to define the kernel, you need to define it like with a certain number of neighbors, right? Do you already have 3 neighbors, 4 neighbors, or 2 neighbors? Like, that's my question. Because you are interested by chirality, you always have 4 neighbors.
Oh, you mean the degrees? Yeah. So the if you look at a center atom, then we only look at one hop neighbor. So we only need to look at different degrees. So we have degree 1, degree 2, degree 3, and degree 4. Yeah. And
So
for each
for
each degree, we may have multiple kernels.
Okay, I see. So you have different kernel per degree.
Yes. Yes.
Okay.
Yeah.
Perfect.
So you can learn different patterns. Yeah. As you can see here, we have 3 dots here indicating more kernels.
Okay. Perfect. Thank you.
Yeah. No problem. Okay. Now let's move on to the evaluation part. So first, let's look at our data sets. First, we look at some commonly used data sets in the GNN community. And we found those data sets are probably not ideal for benchmarking our data sets, our method, for the following reasons. First of all, they may have a limited number of data. And secondly, they may not do pre-processing to remove some experimental artifacts, which I will talk more about this later. And finally, they may not be relevant to molecular activity against some therapeutic targets. I see a question in the chat. Okay, based on every atom, just the backbone of the molecules. Based off every atom, this is small molecule, this is not protein, so we don't have so-called backbone. Yeah, so it's based off every atom. So for the atom, we consider a center atom and or it's one hop neighbor. It's like a star kind of structure. Yeah. Okay. Let me see in the chat. Okay, cool. Yeah. Okay, let's back to this data set. So for these are some reasons for why we didn't use some common data sets in the GNN community. So so what data set should we use? Okay, as we mentioned earlier, our training data comes from this high throughput screening. So we want to use the experimental data from the high throughput screening. So what are those data look like? So here is a typical output from the primary screen of the high throughput screening. So as you can see here, usually we can get a large number of inactives and a few actives. And for those actives, we need to go through more rigorous several rounds of confirmatory assays, which takes more time. But because we only have a much less number of actives, we can do more fine-grained experiments, and then we can get some confirmed actives. But to notice here, for those primary screens, usually they set a very loose activity threshold so they can reduce the false positive rate, meaning that they don't want to miss any possible actives for the further investigation for the following conformatory assays. So this just means that the result from the primary screen has a very high false positive rate. So if we directly use the result from the primary screen, that's going to be problematic. That's what I mean earlier by if we don't do some pre-processing to remove the experimental artifacts, that's problematic. So we need to use some well-curated data sets that can relate the primary screen to the following conformatory assays and only look at those confirmed actives. So we will use those well-curated data sets from Bukiewicz paper from 2013. So these data sets originally are from the PubChem database. Here they are specified by their PubChem AID or assay ID. And these data sets, they feature in several things. First, they have at least 150 confirmed active compounds. So they are well curated. Secondly, it features on diverse target classes. As we can see here, we have GBCR, ion channel, transporter, kinase, and enzyme. It covers most of the important target classes. And finally, these data sets also feature in their realistic characteristics. First of all, it has a large number of molecules, as you can see here in the highlighted square here. And also, it has a very imbalanced label. This imbalance of label results from the very low hit rate we mentioned earlier. Earlier, we said that the rate of finding active compounds is usually less than 1%. So this is also reflected in these data sets. So these data sets are challenging and realistic for evaluating our methods. And also, as a note, these data sets are now made available at the Therapeutics Data Commons, also known as TDC. TDC is a Python library that makes downloading and the use of those data sets much easier. Okay, that's the data set. Now we are going to look at our evaluation metric. I see a question. Those data are still prime. These data sets are not just a primary screen. They actually relate the primary screen to their corresponding conformatory assays to have the conformed actives. Yeah. So now let's look at the evaluation metric. Okay. Evaluation metric. So in a real-world drug discovery campaign, so once we have those predicted activity score, so what we really do is only take a look at those predicted active ones, and we don't care about those inactive ones because only those predicted to be highly active molecules are going to be synthesized, purchased for the further experimental validation. And those predicted to be inactive, whether we predicted wrong or right, we just don't care. So in order to capture that characteristic, we use the ranged log AUC. So basically, compared with the traditional AUC that integrate over all false positive rate, we only look at the very small false positive rate range. So this small false positive rate corresponds to a very high activity cutoff. So by integrate over only a very small false positive rate range, we bias towards the performance of these top ranked predictions. And following previous example, we choose false positive rate to be 0.001 to 0.1. And for the perfect classifier, it gets log AUC in this range equals to 1. And for a random classifier, we get a range the log AUC around 0.02. Yeah. Then let's talk about our baseline models. First, we benchmark our model against the 3D graph neural network. So here, 3D graph neural network basically means that instead of using the chemical bonds as the edge, here they look at their neighbors in the 3D Euclidean space. We also benchmark it against some chirality-aware models, like the one we showed before. And finally, we also benchmark our model against architecturally similar methods like this GNN, which also which use graph kernel to measure the similarity between the subgraph and the filter. So here is our results. So here we list our model in the first column and the benchmark data sets in the following columns. And as you can see from the results here, so our methods achieve the best average range of the AUC. And also, if you look at the average rank here, our method also achieved the lowest average rank between all these data sets, followed by these 3D GNNs. And we also not only look at the domain-specific metric range log AUC, we also take a look at a more general metric like the AUC. And as you can see from the results here, our method also performs on par with other baseline methods. And here, it leads us to wonder, why could our MolKGNN perform better than the 3D GNNs? Here we provide an explanation. So for a 3D molecule, if we use a 3D GNN, we can get some 3D geometric information, for example, like atomic pairwise distance in the 3D space. However, these 3D geometric information will be different if we look at different conformation of the 3D molecule. So there is a question to only use the high binding activity to train and validate. Can these be too long? We will use both the active and inactive molecules for the training. Yeah, so it's a binary classification problem. So it's a highly imbalanced binary classification problem. Yeah, and we for the training we did some weighted cost. Yeah. Okay. Back here. So for the certain 3D molecule, it does not just exist in one conformation because we have rotatable bonds. So if we rotate that single bond, it can actually change into different shape or different conformation. So if we use 3D GNN, it will give different 3D geometric information. However, for these 3D conformations, usually only a few binding conformations that accounts for the activity for certain targets. And the remaining non-binding conformation, they actually could be detrimental to the activity prediction. So if we happen to use those non-binding conformation, then that could give us a worse result. And usually the scenario is we don't actually know which ones are the binding conformations. So in this case, our MolKGNN as a 2.5D model, meaning that we don't use the 3D Euclidean distance, and we have the 0.5 as the chirality sensitive module. This MolKGNN has the advantage in this case. Yeah, this is for the main result, and we also take a look at one of the main benefit of our method, the interpretability. So first, let's talk about how to look at trained patterns in our kernels. So as we said earlier, once we have a molecule, we can look at a patch of this. And this neighborhood, it has all the attributes associated with the atoms. And usually we do not want to use these attributes directly. We go through some transformation. And here I call it an encoder. So we use some encoder to transform those attributes into some embedding space, have some atom embedding. Then once we do the molecular convolution, as we said earlier, we can learn some attributes, just like in image convolution. The question is, how do we interpret those embeddings? We don't know what these means. So we train a decoder. The way to train it is simple. So we have a set of known elements, and we use the same encoder from our main model, and we convert them into the atom embedding. And then we train a decoder to convert it back to the known elements. And once we have that, we can use the decoder to translate those embeddings back into our kernel pattern. So once we have these kernel pattern, we can start look at them. And here I show an example. Here I show the translated kernel pattern of a center carbon surrounded by 3 fluorine atoms and also another 1 carbon. And if we look at our training example, we can find there are actually several examples of molecules showing this pattern. And here I listed 3. And this actually aligns with the domain knowledge. This pattern is known as an important substructure in the medicinal chemistry known as the trifluoromethanol group. So this example highlights our method of being having a practical interpretability and having a practical value. We also do some ablation study on the subscores. First, on the left, we have our ablation study evaluated by the ranged log AUC, and on the right, we have it evaluated by the traditional AUC. As you can see from these 2 figures, so on the left, we can see removing any of these 3 components, the center subscore, neighbor subscore, or the edge subscore, has a negative impact on the performance. For the AUC, we found that removing the center or the neighbor subscore has a negative impact on the performance. So here, we think maybe the edge features are possibly more informative for identifying active molecules. This actually corresponds to the fact that some of the 3D graph neural network, they only look at, they only view the molecules as a 3D point clouds. They do not even consider the edge at all. So that probably means the edge subscore is not so useful in those general metric. Finally, we also did our ablation study on the number of kernels. So previously, Prudential also asked about the number of kernels in each degree. So as you can see here, we plot both the ranged log AUC and the AUC here, and both of them show a similar trend. So the performance increase to a certain point while you increase the number of kernels in each degree. And after a certain point, it goes into a plateau. So this is because in the beginning, we need more kernels to capture the similarities to different molecular neighborhood. So these kernels are kind of like the anchors in the similarity space. So they basically, you can have those anchors to measure how similar a molecular neighborhood is to the kernel. But once you reach a certain number of kernels, then adding more kernels, they just do not have increase the basis of this space. So this performance just goes into a plateau. So it has a little impact on the performance. A question in the chat. Oh, okay, yeah. So yeah, and here we come to our conclusion. So in this work, first, we introduced a novel interpretable molecular convolution. We named it MolKGNN. It has a new convolution operation, and we also used a better chirality characterization, which is a light-weighted one. Use just a linear algebra for a calculation of the orientation. And then finally, we also did a comprehensive evaluation for the computer-aided drug discovery. We have well-curated data sets. We have domain-relevant metric for evaluating our method. For some possible future directions of this work. So first, as we said earlier, right now, this work only look at chemical bonds as the edge. Possibly, we could extend it to 3D models, and it could be useful for proteins, because usually for those proteins, if you look at those residues, and you don't just want to look at their chemical bond connection, but maybe their 3D Euclidean space neighbors. And possibly, we can design more complicated kernels beyond just one hop neighbor for enhanced interpretability. And finally, we can evaluate our method on more molecular data sets rather than just drug discovery related data sets. With that, I'd like to thank my advisors and my founding agents. And finally, I'd like to thank you all for your attention. If you have any questions, I'm happy to take them. Thank you.
Perfect. Thank you so much for the great talk, Lance. There is a question by Duke in the chat. Does the number of kernel impact the inference time?
Does the kernel impact the inference time? The number of kernel, yeah, definitely. Yeah, if you have a large number of kernels, yeah, it will impact it. But as we show in the ablation study, once you reach a certain number of them, you don't need to keep increasing them. And one thing about this is that we earlier also tried to use some to enforce some diversity between kernels, so that we try to force the kernels to be different. But then we found that the performance will not go into a plateau, but we'll have a sweet point. For example, the kernel having a number of 5 will have the best performance. That will just make the tuning of these number of kernels more difficult. So that's why we do not use that enforcement of the diversity of kernels. So the kernels could be learned to be similar or the same.
Perfect. I want to go back to the explanation, the explainability study that you did. And I was wondering why you didn't use the classical method for CNN, like where you do kind of a gradient ascent to kind of figure out what part of the image is responsible for the prediction. And and how does this compare to this? Because like I have the feeling that using the decoder is also prone to some other errors.
Yeah. Can you still see my slides, by the way?
Yes.
Okay. The first question basically, why don't we use image-like convolution, right?
The image-like interpretation when it comes to determining which part of the molecular graph is responsible for the activity.
What do you mean by image-like interpretation?
GraphCam, for example, GraphCam is one of the methods that people use for image interpretability, like image prediction interpretability.
So here, if we have the trained pattern here, we can directly look at their.
We are seeing your Slack instead of. Yeah.
In the what?
We were seeing your Slack instead of your presentation.
Oh, sorry. Let me see. Can you share this again? Here, now you can see it?
Yes, thank you.
Okay, yeah. So here, these patterns in the kernel, they are more readily interpretable. So like shown in this example here, we by just looking at this, we can directly know there are 3 fluorine surrounds 1 carbon, and there is another carbon also as the neighbor. So we don't use a traditional image convolution because first, image convolution, they are like pixel-like, so they are in a discrete space, and also they are not rotation invariant. But the molecules, no matter how you rotate them, they always they are always of the same identity.
Yeah, I believe my question is slightly different from that. It's not about using the CNN convolution, but rather on the interpretability side, you were kind of encoding and decoding all combination of atoms, and that's what you use to infer what kind of part of the graph is responsible for the activity, instead of using a classical gradient ascent method, a GraphCam, to actually figure out what part of the graph is responsible for the activity. And I was just wondering, what's the reasoning behind that? Like,
Gotcha. Oh, yeah. So, yeah, there are indeed different ways of interpretation. For example, like you mentioned, the gradient-based methods, or they can look at those weights. Yeah. So we introduced a new way of looking at the interpretability. So these encoder, decoder part, they are actually just additional steps. But the key part is actually just using this convolution for it to learn a pattern encoded in the kernel. So just like in the image example, in the image convolution example earlier, when we look at an image convolution, we could just directly look at those patterns. And those patterns, they actually make more sense in human eyes, like the face detection example earlier. Then human can immediately recognize, instead of just looking at some weights or the gradient, which are just numbers.
okay, I see. Cool.
Yeah.
Another question is, when you were benchmarking, I remember in the Cairo method and the care method, they introduced some data set that they were rather sure convinced that chirality plays an important role. Did you benchmark against those data sets to see if your method kind of outperformed those ones?
Which ones you mean?
Yeah, in the paper for the Adams and Feng introduced different data set, smaller data set, but like, did you compare against those?
We actually also did one data set for chiral molecules. Basically, contains pairs of mirror image molecules, and you for like some very basic GNNs like GCN, they just achieved 50% of accuracy because either they just cannot distinguish the mirror image. And for our method, we can achieve like 99 point something. So basically, it's close to 100%. Yeah.
Okay, I see. Cool. Any other question in the audience? If so, please just open your mic and jump on in.
Sorry, I have a question. Can you hear me?
Yes.
Yeah, sorry, I'm not familiar with this line of work, so the question is kind of naive. So I'm not sure I understood, when do you run the encoder? Because you do this message passing with the kernel features, but when do you run the encoder then?
Oh,
I'm not sure, compared to the message passing, which only uses the convolution results.
Gotcha. So the encoder just some pre-processing for transforming your initial features into some latent space.
Oh, so these are the features then are used for convolutions?
Yeah. After the encoder, it just becomes the actual feature used for the convolution. Yeah.
Okay, and then you decode once you converged.
Yeah. Once you have the once you trained your kernel, the kernel will learn to be similar to some of the patterns frequently seen in the training samples. But these trained vectors, they are in the latent space. So if we just directly look at them, we don't know what this means. So we need to translate them back into like those atomic identities, so we know which atom those are.
Okay, so the decoder is just some MLP.
Decoder, yeah, for our implementation, yes, we just use MLP.
Okay, I got it. Thank you.
Yeah, no problem.